In this lesson, we're going to look at conversions between mass and particles. So if you have the mass of a substance, you can determine how many particles it contains, or if you have the number of particles of a substance, you can figure out what its mass would be. So let's look at the calculations we've covered so far in other lessons. So we have talked about how you can convert from particles to moles using Avogadro's constant, right? So there are 6.02 times 10 to the 23 particles in every mole. So we can use that number to convert between particles and moles. We've also looked at how we can convert between moles and mass using the molar mass. So whichever element or compound you're talking about in the question, you can use its specific molar mass to convert between moles and mass. So what we're going to do is we're going to put those two things together. So how can we convert from mass to particles or particles to mass? So we can't go directly in one step. We have to go through moles. So if we have particles, we need to convert to moles using Avogadro's number. Once we're at moles, we can then convert to mass using the molar mass for that specific element or compound in the question. Or we can go the other direction. If we start with mass, we can convert to moles using molar mass, and then to particles using Avogadro's number. But we know that there are different types of particles, right? So from moles, we can go to the different types of particles. So we can have molecules or formula units, or we can have atoms. And which one we go to and how we get there depends on what the substance is. So if the substance we're talking about is a monoatomic element, then we can go directly from moles to atoms, because the atom is the particle that makes up that element. So we can go directly from moles to atoms using Avogadro's number if the substance is a monoatomic element. However, if the substance is a compound, when we use Avogadro's number, we're going to be finding the number of molecules if it is a molecular compound containing covalent bonds, or we're going to be finding the number of formula units if we're talking about an ionic compound. So when we use Avogadro's number here, we're finding the number of molecules or formula units. If we then wanted to find atoms, if we had a substance that was a compound, we would then have to use the atomic ratio from the compound's formula. So we're going to look at several examples, and we're going to use this roadmap to help us figure out how to solve the problem. So we're going to have our little roadmap up in the corner there. So our first sample question, how many atoms are in a 5.0 gram sample of pure gold? So now let's look at this question. How many atoms? So we're going to end at atoms in our map. Okay, how many atoms are in a 5.0 gram sample? So grams, that's mass. So we're going to start at mass. Now, how are we going to get from mass to atoms? Well, the next thing we need to figure out is this substance an element or a compound? In this case, it's a monoatomic element, gold. So we can go from mass to moles and then right to atoms. So now let's solve this problem. So we're starting at mass. So the first step is we need the molar mass. So the molar mass of gold, which we can get from the periodic table, is 196.97 grams per mole. So when we go to solve the problem, we're going to start with the value given in the question, and that was 5.0 grams. And we're going to follow our roadmap. So we're starting there. So now we're going to use the molar mass as a conversion factor to find moles. Because we're trying to find moles, mole needs to go on the top of the conversion factor. Okay, so we have 1 mole over 196.97 grams. So the grams cancel. We've now reached moles. Next, we're going to go to atoms using Avogadro's number. Because we're trying to find atoms will be on the top of the conversion factor. So we've got 6.02 times 10 to the 23 atoms in 1 mole. So moles cancel. The unit we're left with is atoms, which is what we were trying to find. So now we're going to do 5.0 divided by 196.97 times 6.02 times 10 to the 23. When we do that, we get an answer of 1.52815 times 10 to the 22 atoms. Now for our final answer, we need to check our significant figures. The number we're given in the question, 5.0, only has 2 significant figures, so that's what we can put for our answer. So our final answer is 1.5 times 10 to the 22 atoms. Okay, now let's look at another example. What is the mass of 4.72 times 10 to the 23 formula units of chromium-3 iodide, CRI3? Okay, so let's look carefully at the question. What is the mass? So we're going to end at mass of 4.72 times 10 to the 23 formula units. So we are starting at formula units. And this is a compound, right? So that's just a good check. It's a compound, so we do want to have formula units. So we are trying to get from molecules or formula units, in this case formula units, to mass. So we need to go through moles. So that's the path we're going to take to solve the problem. So in one of our steps, we're going to need the molar mass of chromium-3 iodide. So we'll find that first, right, by taking 1 times the molar mass of chromium and then 3 times the molar mass of iodine, adding them together. So we get 432.70 grams per mole. So now we're starting with the number given in the question, and we're going to find the mass by first converting it to moles. So we've got 4.72 times 10 to the 23 CRI3s, or you could put formula units there. So our first step is to convert that into moles. So we know that there are 6.02 times 10 to the 23 chromium iodides in 1 mole. So now we've reached moles. So now we can find the mass by using the molar mass. Because we're trying to find mass, the grams goes on the top of the conversion factor, 432.70 grams over 1 mole. So then you put in your calculator 4.72 times 10 to the 23 divided by 6.02 times 10 to the 23 times 432.70. And you get 339.2598 grams. Check your significant figures. You need to have 3. The smallest number in the question is 3. So this becomes 339 grams. Next question. How many carbon atoms are in a 500.0 gram sample of octane, which is C8H18? So how many carbon atoms? So we're going to end at atoms, are in a 500.0 gram sample. So we're going to start at mass, and this is octane. So this substance is a compound, C8H18. So we have to follow the path that goes through the compound, the molecules and the formula units. So we're going to convert to moles using the molar mass. Then we're going to convert to molecules using Avogadro's number. And then we can go to atoms using the atomic ratio. So to start off with, we're going to need the molar mass of octane, which is going to be 8 times the molar mass of carbon, plus 18 times the molar mass of hydrogen. Add those together, 114.26 grams per mole. So now we can find the number of atoms, but first we have to convert to moles and then to molecules before we can get to atoms. So as always, we start with the value given in the question, the 500.0 grams, and we're going to follow our map. So we're starting at mass, so our first step involves molar mass. We're trying to find moles, so the 1 mole is going to go on the top of the conversion factor. and the 114.26 grams on the bottom. So now we're at moles, so our next step is to go to molecules. So we're going to use Avogadro's number, and the 6.02 times 10 to the 23 is going to be on the top because we're trying to cancel out moles on the bottom. So there are 6.02 times 10 to the 23 octanes in 1 mole. Okay, so now we've figured out the number of octanes, but this question is asking for the number of carbon atoms. So then we need to set up a ratio using the formula. So how many carbon atoms are there in 1 octane? Well, there are 8, right? C8. So we say that there are 8 C atoms, that's the top, in 1 C8H18. So the C8H18s cancel. So then in your calculator, you do 500 divided by 114.26 times 6.02 times 10 to the 23 times 8. And when you put that all in, you get 2.10747 times 10 to the 25 atoms. And then you need to check your significant figures. Okay, the smallest number actually comes from Avogadro's constant, the 6.02. That only has 3. Remember that the 8 C atoms is a accurate value. Right? It's counted. There are exactly 8 C atoms, so it has infinite significant figures. So our final answer needs to have 3, so 2.11 times 10 to the 25 atoms. Okay, one last example question. Determine the mass of a sample of pure water that contains 5.2 times 10 to the 24 atoms. So we are determining the mass, so that's where we're going to end up. A sample of pure water. So water is a compound, right? So we're going to go through that compound path that contains 5.2 times 10 to the 24 atoms. So atoms is where we're going to start. Because it's a compound, we have to go to molecules first, then to moles, and finally to mass. So in order to do this problem, we're going to need the molar mass of water. So water is H2O, 2 times the mass of hydrogen, plus 1 times the mass of oxygen, gives us 18.02 grams per mole. As always, start with the number given in the question, which was atoms. And then we can find the mass after first converting to molecules and then to moles. So we're going to start with 5.2 times 10 to the 24 atoms. Our first step is that we need to get to molecules. So we need to find the number of water molecules. Well, we know that there are 3 atoms in every 1 H2O. So atoms have canceled. Now we've reached molecules, H2Os. So the next step, according to our map, is that we need to use Avogadro's number to convert to moles. So there are 6.02 times 10 to the 23 waters in 1 mole. So the waters cancel, and we're left with mole. Finally, we can convert from mole to mass using the molar mass of water. The molar mass, the 18.02, is going to go on the top of our conversion factor, and the 1 mole on the bottom. Moles are going to cancel, and we're left with mass, grams, which is what we wanted. So now in your calculator, 5.2 times 10 to the 24 divided by 3 divided by 6.02 times 10 to the 23 times 18.02 gives you 51.8848 grams. Now we look at our significant figures. The smallest one is 2, has 2 significant figures, that 5.2 times 10 to the 24. So that becomes 52 grams. So when you're solving these different types of problems, keep in mind this roadmap. Look at it when you're starting out. You'll get more used to it as time goes on. But figure out where you're starting, figure out where you're ending. Look at whether this substance is a compound or a monatomic element, and then follow the appropriate path.